general solutions of equations. So if we want to solve sine theta equals some number, just call it x. Now normally we'd say, okay, well which quadrant's it in and things like that. That all depends on whether x is positive or negative. So if x is greater than 0, I know that it's in the first quadrant. The acute angle would be whatever the inverse sine of x is. Or in the second quadrant, again, the acute angle would be the inverse sine of x. So therefore my two answers would be, okay, well it's either going to be the inverse sine of x or pi minus the inverse sine of x. Okay. Well, what about if it's negative? If it's negative, now this time the acute angle won't be the inverse sine of x. It'll be the inverse sine of negative x. Because remember, we're saying x is a negative number. So to get the acute angle, we need a positive number. So it'll be the inverse sine of negative x is the acute angle, and over in the fourth quadrant. So we would get pi plus the inverse sine of negative x, or 2 pi minus the inverse sine of negative x. But then we can use our rule, because remember the inverse sine was an odd function. So pi plus the inverse sine of negative x is the same as pi minus the inverse sine of x, which is actually the same answer as we got when it was greater than 0. The other one becomes 2 pi plus the inverse sine of x. And if you think about that, 2 pi plus the inverse sine of x, well that's the same as just inverse sine of x, because you've gone around the circle once. So in fact it does not matter whether it's positive or negative. We get the same answers. So that now allows us to generalise a solution. Because if you look at the pattern, we've got inverse sine x, pi minus inverse sine x, 2 pi plus inverse sine x. The next one would be 3 pi minus inverse sine x, and so on. So we've got that alternating pattern. So inverse sine of x, we're going to get multiples of pi, and then it'll be plus or minus. So we're alternating, and that's where we put that minus 1 to the power of k in, so we can take into account the alternating of inverse sine x. That allows us to generate every possible solution. Let's do the same for cosine. Let's see what happens. So if x is positive, well in that case we're in the first quadrant or the fourth quadrant. Acute angle would be inverse cos of x. So we get inverse cos of x or 2 pi minus inverse cos of x. But if x is negative, I should say, if x is negative, we're in the second quadrant or the third quadrant, but now we want the inverse cos of negative x to get the acute angle. So we'll have pi minus the inverse cos of negative x, or pi plus the inverse cos of negative x. Our rule for inverse cos of negative x, well that was our odd function that had been shifted up. So we ended up with pi minus. So the first one becomes pi minus inverse cos of x. That's just the inverse cos of x. Same answer as the first one. Second one becomes pi plus pi minus the inverse cos of x. 2 pi minus inverse cos of x, again, same as the first one. So once again, it does not matter whether x is positive or negative. So to generalise this one, the pattern's going to go inverse cos of x. The next one will be 2 pi minus inverse cos of x. After that, go around the circle, we'd get 2 pi plus the inverse cos of x. Then 4 pi minus, then 4 pi plus. So we've got 2 pi k plus or minus inverse cos of x. Alright, let's complete the set. Let's look at tan. So x is positive. We're in the first quadrant or the third quadrant. So inverse tan of x or pi plus inverse tan of x. If x is negative, second quadrant, fourth quadrant, but again we're talking inverse tan of negative x in this case. Pi minus inverse tan of minus x, or 2 pi minus inverse tan of minus x. Inverse tan was an odd function, so we end up with pi plus the inverse tan of x. Oh, same as this one. 2 pi plus inverse tan of x. Well, same as the first one once we've gone around the circle. So this pattern is going to go inverse tan of x, pi plus inverse tan of x, 2 pi plus inverse tan of x. So basically, we're talking multiples of pi plus the inverse tan of x. Now, those formulae, I better check before I tell you a lie. No, good, they are there. Thought they were. They are on the reference sheet. So if you should go, oh, hang on, which one is it? You know, use that to your advantage. Okay, so sine theta equals root 3 on 2. We go, okay, there's my general solution. Pi k plus, this is the one where we have to take into account the alternating. So minus 1 to the power of k, inverse sine root 3 on 2, where k is some integer. Now in this case we can tidy that up because we know what the inverse sine of root 3 on 2 is. So we get pi k plus minus 1 to the power of k times pi on 3. Now if for some insane reason we wanted to solve the equation between 0 and 2 pi, I say for some insane reason because why would I be using general solutions if I'm finding solutions between 0 and 2 pi? But let's just say we did. We've got the general solution. How do we then generate our answers? Well, we just keep subbing numbers in. So I'll start at 0 when k is 0, 0 pi, yeah. So minus 1 to the power of 0, well that's 1. So pi on 3, my first answer. Sub in 1, I'll get pi minus pi on 3. Oh, that's 2 pi on 3. Am I sure whether it's finished or not? Okay, well k equals 2 would be my next one. 2 pi plus, oh hang on, as soon as I'm saying 2 pi plus, I know I'm outside the boundary, so yep, okay, I've got my solutions. Let's do a cos one. Now cosine was one that goes 2 pi. So be careful with that, because the other two, remember, are pi k. The inverse cos is 2 pi k. So 2 pi k plus or minus inverse cos. But this is inverse cos of negative 1 on root 2. Okay, well inverse cos, that had a range going from 0 to pi. So we're talking about an obtuse angle there. As opposed to inverse tan, inverse sine, it would be a negative acute angle. But this one's an obtuse angle. So we get 3 pi on 4. So there's our formula. Let's generate. Well, if k equals 0, 0 plus 3 pi on 4, 0 minus, well I don't want the 0 minus 3 pi on 4. Then I'll sub in 1, I'll get 2 pi plus, don't want that one, 2 pi minus, yes I want that one, 5 pi on 4, so there's my two answers. Okay, let's do tan. Tan theta 1 on root 3, so that was the pi k, just like the inverse sine, but this one, the sign doesn't alternate, it's just plus all the time. Inverse tan 1 on root 3, pi on 6. Again, if we were finding solutions between 0 and 2 pi, sub in 0 I get pi on 6, sub in 1 I get pi plus pi on 6, sub in 2, 2 pi plus, whoop, too much, I'll stop there. Pi on 6, 7 pi on 6. Okay. The more interesting questions are one like this. Sine theta equals the sine of 5 pi on 7. So tempting to say the answer is 5 pi on 7. Because it makes sense, sine theta, sine 5 pi on 7. But let's generalise it and see what we actually get. Because notice, I haven't put any domain in there whatsoever. Sure, 5 pi on 7 is one possible answer, but there's lots of possible answers that would solve this equation. So we generalise it. Pi k plus minus 1 to the power of k, inverse sine of sine 5 pi on 7. But inverse sine of sine 5 pi on 7 is not 5 pi on 7, or is it 5 pi on 7? That's right, because 5 pi on 7 is an obtuse angle, but inverse sine can only give us acute or minus acute. Now an obtuse angle for sine would be positive, so therefore we're after the acute angle. And the equivalent acute angle would be 2 pi on 7. So there's our formula. It is important you write where k is an integer, because if you don't put that in there, theoretically you could sub in k equals a half or k equals a third, and that clearly would be wrong. The cos of 2x is the cos of pi on 9. Okay, so again, go to our general solution. 2x this time though is 2 pi k plus or minus the inverse cos of the cos pi on 9. That one we can cancel. Pi on 9 is an acute angle. So that will cancel. So 2x is 2 pi k plus or minus pi on 9. Just like a normal equation, divide both sides by 2. We get pi k plus or minus pi on 18. Alright. Oh dear, excuse me. So exercise 1F. And that finishes off our look at inverse trig. Oh, you know what that means. We get to start tomorrow. Keep steady there. Keep steady.